So, welcome back. In this lecture we continue the discussion on the initial boundary value problem, and now we take the Neumann boundary condition for the wave equation in first quadrant. Okay, so let me again write the problem. So, wave equation, one dimensional wave equation in the first quadrant. Initial conditions, UTX0 U1 x, again x on the positive real axis, and now we consider the Dirichlet boundary condition. So, u0, u1 and h are given functions with appropriate smoothness. So, now let us try to find out a formula for this solution and how, and see how it differs from the earlier formula for the Dirichlet problem, where u0 the value of the solution on the boundary was provided. So, the general mixed, let me just remark before mixed boundary value problem. So, if we prescribe a condition of this form, because of the linearity in the equation and because of the linearity in the boundary data, we just concentrate on the Dirichlet Neumann boundary condition. So, this is Neumann condition, boundary condition. So, again the idea is same. So, again you just consider the first quadrant, and this characteristic x equal to C t. So, again in this region the solution has domain of dependence completely lying on the positive real axis. So, the solution again is given by D'Alembert's formula. There is absolutely no problem there. So, again problem comes here. See, in the previous case of Dirichlet boundary condition, we could use characteristic parallelogram property because the value of the solution was given on this boundary line. But in the present case, we are not given the value of the solution, but its first derivative. So, we cannot use CPP here, we cannot use characteristic parallelogram property. So, we have to proceed slightly different way, and that I will show you. So, again let us concentrate what happens in this region. So, x is less than C t. So, there is absolutely no problem in the region x bigger than C t. The general solution again we depend on that now. So, general solution So, u x t is given by f of x plus c t plus f of g of x minus c t. So, as we did in the case of D'Alembert's formula, so again in the region x equal to x bigger than c t. So, we just use the initial conditions. So, as before, so let me write it. So, you just check, this is what we did earlier, u 0 x plus 1 by 2 c 0 to x u 1 y. So, we can always put a constant here k 1, and now this is valid only for x bigger than 0. Okay. And g is also similarly given here. So, g of x, so let me write it, minus 1 by 2 c minus k 1. Okay, that is how in this region. So, x is bigger. So, x bigger than c t means x minus c t is positive and x plus c t is positive anyhow. So, this we can use this f and g in terms of the initial data and compute the solution. So, what happens when x is less than c t? Okay. So, we still have the general solution, no problem there. F of x plus c t plus g of x minus c t. So, x plus c t is positive. So, there is no problem. So, again we can use this formula for f, but when x is less than c t, so this is negative, and this formula does not provide us with an expression for g. So, we have to now invoke the boundary condition in order to find this g. So, that is the only difference between the Dirichlet boundary condition and Neumann condition. So, here we have to do little more work, but we are given u x not u. Okay. So, let us calculate u x from this. So, u x, so let me calculate at a general point. So, this is f prime x plus c t, and that is g prime x minus c t. And using the boundary condition, we therefore get, so h of t is equal to f prime at c t plus g prime at minus c t. Okay. So, therefore, g prime of minus t equal to h of t minus c minus f t f prime t, and f is already known. Okay. So, just remember that. So, f is already known, because here also it is positive. So, for f is known. So, you just take f prime there and substitute here and do one more integration. So, there is a minus sign. So, you just watch for that thing. So, we get g of minus t is equal to, let me write it, minus 0, this minus is coming because of that minus 0 to t h of s by c ds, and this I simply get f, and I just substitute the, again there is plus because of this minus. Okay. So, that you have to just observe. Okay. So, it's, the signs are important. Okay. So, we just, so we can always add an constant of integration. So, k is just an integration of constant, and now this is valid for t positive. Okay. So, we have obtained now an expression for g of minus t when t is positive. Okay. So, again go back, this is our expression, this is our expression, you simply substitute that. Okay. So, therefore, for x less than c t u of x t. So, let me just write that. So, this is just f of x plus c t plus g of x minus c t, and this is just let me write once again. So, this is half of u 0 x plus c t plus u 0 x, just a minute, just a minute. So, again go back, so this is very important. This is the expression for f of x. So, I am replacing x by x plus c t. Okay. So, just remember that. Plus 1 by 2 c 0 to x plus c t u 1 y dy. This is for f, and now, so this is minus t. So, I write this as minus c t minus x, that is positive. Okay. So, just you get minus 0 to c t minus x h of s by c ds plus half of u 0 c t minus x plus 1 by 2 c 0 to c t minus x u 1 y dy plus a constant of integration. Okay. So, let us now there is half u 0 x plus c t there plus half there, and now these two integrals 0 to c t minus x, and they cannot be combined. Okay. So, that is c t, of course, we can still do that c t minus, but this is a plus there. Okay. So, there is no cancellation there. So, that is one important difference. So, we will just write the final formula. So, therefore, for x less than c t, u of x t is equal to. So, first let me write the boundary data. So, this is c t minus x h of s by c ds plus half u 0 c t plus x plus u 0 c t minus x. And now we have this half 1 by 2 c 0 to 2 integral c t minus x. So, let me write that also here 0 to c t plus x. There is no cancellation here. So, you have 2 integrals here of the same function, integrand is same. Let us briefly write that, and there is always a, see earlier that was not there. So, now there is a constant of integration. Okay. So, then this is valid for x less than c t. Okay. So, this term is similar to one in the D'Alembert's formula, there is no change, but there is slight change in the integral. Okay. So, it is more this part is more like D'Alembert's formula, and this is coming from the boundary term. Okay. Again, so it is more work and more algebra. So, you can find out in this case what are the compatibility conditions. I am not going to do that. So, you just, because now you have the again expression for the solution, one in the region x bigger than c t and another one for x less than c t, and now you again take the limits of the solution, its derivatives, okay, and try to find out what are the compatibility conditions. It is more algebra. I am just compatibility. Okay, that just you work out. Okay. So, finally, just make wave equation in a finite interval. See, all these developments eventually lead to wave equation in a finite interval. Let me state the problem again. So, now again the wave equation, and now x lies only in a finite interval. So, call it 0 L. So, we can always bring any finite interval into this form. So, let us instead of writing a b. So, we will just write 0 L. So, again initial conditions u t x 0 u 1 x, x is in the interval 0 L, and now there are two boundary points. So, we have to provide 0 t. So, let me call it h 1 t, simplicity again Dirichlet boundary condition. So, you can also take Neumann boundary condition, h 2 t. So, this is case of a finite string which is placed on the interval 0 L. Okay. And some initial profile is given and initial velocity is given in the string, and now so you provide the data here. Okay. So, here it is h 1 t, h 2 t. Generally, such problems are approached by Fourier method, which is same as separation of variables. So, you seek a solution in the form of separation of variables, and then manipulate and then try to get the Fourier series expansion. Okay. That is why it is Fourier. I will show you an example. But let me here describe this method generally requires more smoothness. I will show you, and some nice formulas do not yield C2 solution, requires more smoothness on the data. Be it initial conditions or boundary conditions. Okay, we will see that. So, let me show you here quickly how we approach this problem just using the characteristics, and how a solution can easily be obtained. So, though no explicit formula can be written in this case, but depending on t we can determine how the solution is determined. Okay. So, let me write again this zero L, and now you draw the characteristics. So, let me just use different color. Through these points and keep on doing that. So, let me just okay. So, these are characteristics. And you see how the characteristics play an important role in determining the solution of the wave equation in several different problems. So, we saw it on the entire real line, first quadrant, and now the finite interval. Okay. So, let me call them 1, 2. So, this infinite cylinder, if you want to call this infinite rectangle, so is divided into several regions. So, now depending on where the point x t lies, the solution is determined in different ways. For example, if this belongs to the region 1, that is the first one. So, here its domain of dependence is lies on the interval 0 L, and so in region 1 we can simply use D'Alembert's formula. And in the region 2, now one characteristic hits the boundary line x equal to 0 and another one comes to the first region. So, we can repeat the argument in the case of Dirichlet problem for the quadrant. So, we can obtain a solution in region 2 using the boundary data only on x equal to 0, and similarly in region 3. And as you go up, okay, so there will be more interaction between both the boundaries, and in principle we can obtain a formula at any point x t, okay, though it there is no simple formula to write down for any x t. It depends, first we have to find out in which region it belongs to, and then we have to work backwards till we get to the region 1. Okay. Though we are not able to write explicitly, but still there is a procedure how to obtain the formula, and here we do not require more smoothness as compared to Fourier series, that I will briefly discuss next time. And again, suitable compatibility conditions, now there are two interaction points 0 and L need to be determined in order to show that the solution is a C2 function in the entire region. Otherwise, if the compatibility conditions are not satisfied, then u or its derivatives will not be continuous across this characteristic. Now, there are plenty of characteristics. So, earlier there was only one, now there are many characteristics. So, with that thing I will come to an end of this talk. So, next time I will show you how Fourier method is applied and what are its limitations, and also show you some examples. Thank you.